it is me, Maria Sandoval, and today I will be talking to you about the quantum theory a bit. First, we're going to be talking about the wave nature of light. So, visible light is a type of electromagnetic radiation. The wave properties of electromagnetic radiation are described by three variables. Frequency, which is shown by the lowercase n, gives us our cycles per second. Wavelength, shown by the letter L, gives us the distance a wave travels in one cycle, and amplitude gives us the height of a wave crest or the depth of a trough. So the speed of light is a constant. Here you have our c equals frequency n times L, wavelength, which is 3.00 times 10 to the 8th m over s in a vacuum, meters over seconds. So here is showing the reciprocal relationship of frequency and wavelength. So here, from the top of each of these bridges, basically, is your wavelength. So from the top of this to the top of this, or you could say from the bottom to the bottom of this. So here you can see that we have a long wavelength, we have a shorter wavelength, and we have an even shorter wavelength down here at C. So showing us our frequency is cycles per second. So say that this is a second, this is a second, and this is a second. We see that our wavelengths are extremely different over the two wavelengths. Sorry, it shot me forward a little. So that's how we can show the different wavelengths. You can see that this one's slower, so it's got a lower wavelength. This one's higher, so it's got a faster wavelength. And then our frequency is faster, just like as if it were a longer wavelength, our frequency would be lower. So they correlate with each other. So differing amplitude, brightness, or intensity of a wave. So the higher that the wave is, see here they all have the same amplitude. Here they may not have the same amplitude. You see that this one down here has a lower amplitude and this one up here has a higher amplitude. A lot of times, like, see this light here, you may say that this is pretty dim, but in reality it's just got a low amplitude and you can still see it. It's just not as bright as it can be. So moving on, we're looking at regions of the electromagnetic spectrum. So here we're looking at gamma rays, X-rays, ultraviolet rays, visible, infrared, microwave, and radio frequency. So starting off from 10 to the 8th to 10 to the 4th is your radio frequency. So that's what you're hearing me through right now. That's what you hear on the way to school or work, when you're driving with your radio or your Spotify, whatever it may be, that is a radio frequency that you are hearing from. Moving on, sorry, I have a bit of a runny nose, a bit of a bug. Moving on, 10 to the 6th to 10 to the 8th is your microwaves. So what you use to warm up your food. I'm sure most people have a microwave, and that's the type of wave from the electromagnetic spectrum that you would be using to heat up your food. Moving on is the infrared. A lot of infrared cameras are like what you use on your phone. It's what detects your face. It's what detects your hands when you're going to go wash them in a sink. Infrared is very useful for quite a lot of things. Moving on from that sliver of 10 to the 2nd and 10 to the 14th is your visible region of light. So that's why you can see me, that's why you can see this light, that's why you can see the different colors of the books in my background. Like from here, from 400 to 750 nanometers is what you see. So all the way on the right, 750 is your red, and all the way on the left, 400 is your purple, and right in the middle is your yellow. So moving on, we're seeing our ultraviolet light. Ultraviolet light is used for a lot of things. Some people use it for like skin therapy to make their skin look nice or darker, but a lot of times it can lead to like cancerous things. Ultraviolet light is like what you get from the sun. A lot of people get Some can get cancer, skin cancer, from overexposure to the sun. But some people use it in like tanning beds and stuff, so it's really up to you. X-ray is what you use every time you go to the hospital if you break a bone. It's a really powerful type of electromagnetic wave that helps us see bones and like the inside of your organs. Finally, a gamma ray is like one of the most intense types of electromagnetic rays on the spectrum. Moving on, we're talking about interconverting wavelength and frequency. So, say that a dental hygienist uses X-rays of the L equals 1.00A to take a series of dental radiographs while the patient listens to the radio station L equals to 325 centimeters and looks out the window at a blue sky L equals 473 nanometers. What is the frequency and SI of the electromagnetic radiation from each source? Assume that the radiation travels at the speed of light, 3.00 times 10 to the 8th millisecond. So looking back at the previous one, we're going to want to see, what is this L that they're talking about? They're talking about the frequency of our wavelengths. As you can see at the beginning of the slide, we talk about how we use the speed of light, or it's just talking about the wavelength. We were using the speed of light, which is what they've just brought back into our equation just now. It didn't come out of nowhere. It's the formula for our speed of light. And then our L is our wavelength and our N is our frequency. So moving on with these things that we know how to approach this problem. We want to use our equation C equals NL to convert wavelength to frequency. Wavelengths need to be in meters because C has units of M over S. So wavelengths in units given, use the conversion factors 1 of A equals 10 to the negative 10th M. We're getting our wavelength in M, and then moving on, we're getting our frequency in SI or HS. So here for the X-rays, we have our L equals 1.00. That is 10 to the negative 10 over 1A, which gives us our 1.00 times 10 to the negative 10M. And then we're going to convert that into our frequency that gives us 3.00 times 10 to the 8th SI. Once again, we're converting to our frequency, which gives us 9.23 times 10 to the 7th SI. And then we convert one last time for the blue sky, which gives us 6.34 times 10 to the 14th. Sorry, my computer is just being a little bit slow today. Every time that I try to get it to move on for our questions, it gives me a bit of a problem. Okay, we're finishing off with the energy and frequency. So a solid object emits visible light when it is heated to about 1000 K. This is called the black body radiation. The color and intensity of the light changes as the temperature changes. The color is related to wavelength and frequency, while temperature is related to energy. Energy is therefore related to frequency and wavelength. So E equals NHN. E is our energy, N is our positive integer, and H is Planck's constant. So that is all for today, and we'll be moving on to the extra credit because I would like to do that. So we'll learn a little more about this later on. Thank you so much for spending your time with me, and I hope you learned a lot because I did too. Bye. Have a great night.